In section 2.2, we're going to talk about different ways to describe sets. So the first thing that we need to talk about is what in the world do I mean when I even use the word set? So a set is any collection of objects. So we can talk about your set of music files on your phone. We can talk about your set of textbooks for the semester. We can talk about your set of friends or your set of family members. So it doesn't have to just be things, it could also be people. The elements are the individual objects in the set. So if we're talking about your textbooks, it would include the textbook for this particular class, right? That would be an element in your set of textbooks. If we're talking about your immediate family members, your mom is probably one of those immediate family members. There's two different ways to describe sets. One of them is the listing or the roster method. So this would be the idea of actually writing down all of the things in that collection of objects, that set. So you're just listing all of them out. And that works pretty well if the set's a small set. So most of us could do that with our family members, right? Okay, but some sets are too large to actually even be able to list out everything. And that happens a lot when we describe numbers. If you talked about all of the whole numbers bigger than 5, well, that's not possible. You can't write them all out, right? Like you could put them down to some extent and put the comma ... But that still doesn't really list them all out. So the roster method is a nice way, the set builder notation is a nice way for actually being able to write that down. So I'll give you an example specifically of that one, and we'll just use the numbers bigger than 5. So if you were doing the roster method for the numbers bigger than 5, the best that you could do is you use curly braces. Let me just say that first. Is that you start out with 6 because that's bigger than 5, and I talked about whole numbers. And you would do 6, 7, 8, and maybe you'd even list a few more, but eventually you'd have to do ... and close it off with the other bracket. That's just the best you could do. You might even have to do that if you had the 16 brothers and sisters, right? Okay. Set builder notation, however, it feels a little bit more cumbersome because of the notation. There's just more notation in it, but it's actually a very nice way of describing it. So let me write it down first, and then I'll show you how we read it. So you put an X, you put a vertical bar. Okay, so this is sort of from the top of your line to the bottom of your line on the notebook paper. We want X to be greater than 5, so I write down X greater than 5. And I'm going to say X. I'm going to use a symbol that I'll explain in a minute. This looks like an E, and it is curved. It does not look like a capital E that's a bold-faced typewritten one. It's a curved one. And then we're going to use the letter N with a double line on the left. We're going to get in a lot of this notation on the next slide, but let me just describe what's said on this slide first. This says, there's nothing special about X, by the way. I just chose to use X. You could use any letter you want. So this says all X, this vertical line is read as the words such that. Okay, such that X is greater than 5. Right? You know that one. That's X is greater than 5. This one says X, this E is an element of. Okay, so that's this element's notation up here. It is an element of. It belongs to this thing that follows next. And this thing that follows next is the natural numbers. Okay, we're about to talk about different number sets, but the natural numbers is actually the numbers we're going to start with when we talk about it. So natural numbers are your counting numbers. They're the very first numbers that you learn to use as a very small child. And they would start with what number? 1. When you're very, very tiny, the first thing you learn to count with is the number 1. And those are called natural, or sometimes they're called counting numbers. So if we'll flip to our next slide, we're going to fill in this symbols used in set builder notation. Let me use the first one is this E. This E, and it is curled. Don't use the capital E. That has another meaning in mathematics, okay? So please use the one that looks like it's, I don't know, what do they call that, Denalian, when they make things curvy? It almost looks like that, okay? So this is an element of. So I could say, I am an element of the OBU faculty, and you guys could say, you are an element of the OBU student body. Okay? That would be the idea. And then the next one we already encountered was this N with the 2 lines on the left. And these are our natural numbers. And the natural numbers, I'm going to write each of these out a little bit just so that you remember, are 1, 2, 3, ... They're the numbers that you very first used for counting when you're very, very small. At some point, children start adding and subtracting, or they have to talk about the fact that they wanted to have a candy bar and there are how many candy bars in the house, maybe, and it's 0. And once you introduce the number 0 into your vocabulary, you have created something that's not a natural number. Because natural numbers don't start with 0, they start with 1. So if you actually move into the natural numbers plus 0, you get what are called the whole numbers, and that's a W with 2 lines on the left. And they're very similar to the natural numbers, except they include 0. And in particular, our whole numbers are the ones that we work with in this class until we get to Chapter 5. Chapter 5, we introduce one more type of number, but the majority of the time in this class, we're going to spend working in the whole number system. In fact, much of it we spend in the natural number system.
So does that mean no negatives?
There aren't any negatives in whole numbers, but once we introduce negatives, which is my next one, you have something called integers. And integers use the letter Z. These are the integers. And again, it's sort of like we're expanding our universe a little bit at a time. I remember being in about 2nd grade and somebody doing something that just blew your mind. They said something like, what's 5 minus 3? And I said 2. What's 3 minus 5? And you're like, well, you can't do that, right? You can't. You can't do that in the natural numbers. You can't do that in the whole numbers. So in order to be able to do that, you have to have negatives, and those are integers. So we have sort of this ... starting our list with negative numbers after that, so -3, -2, -1, and then we get all the positives as well, 0, 1, 2, and so on. Those are the integers.
I was getting really excited when I thought you were going to say no negatives.
Well, we won't have negatives till Chapter 5.
Well, that's exciting.
So it's not very, I mean, we have them for like 2 lessons of the whole, like, I think we have 15 lessons in this
That's
class.
positive.
So it's a positive. It's a positive because you don't have negatives.
Yeah.
Okay. This is the extent to where we'll go in this particular class. I want to show you 2 more notations because they do come up periodically, and they will sort of appear at different points, and you should be aware of what people use for them. Let me tell you actually first, the Z is used because it's Latin for integers. That's where the Z is coming from. The reason I, and occasionally you will see I used. It's not used very often because we also have I that's sometimes used for irrational numbers. So it's kind of this ambiguous letter that's not, Z is what's more commonly used. Q is the next one I'm going to do. Q are our rational numbers. So the root word of the word rational is in ratio. And ratio sounds an awful lot like what word? Do you know what a ratio is? Who's taken proportional and statistical reasoning with me? Okay, about half of you have, and you're in it this semester. Ratios are fractions. Thank you, Amy. These are our fractions. So this is anything. This is a terrible way to do this notation, but there's no way to write it out like I just did on the other ones. This is any number that can be written as a fraction. More specifically, it can be written as a ratio of integers. So these rational numbers are items that no matter what they look like in their original form they're given to you, you could write them as a fraction. So like the number 3 is a rational number because you can write it as 3 over 1. Right? You can write it as a ratio of integers. The number 0.7 is a ratio because you can write it as a fraction as 7 over 10. All right? And negatives are fine too. We can write negatives inside of fractions. There's no problem. There are some things that don't count in here though. So there are some fractions that you deal with in geometry in particular. You sometimes encounter them in a couple other places too within mathematics, like pi, right? Once you get pi involved, there's not a way to write that as a ratio of integers. So if you talk about like pi over 2, that's not a rational number. That's what we call an irrational number. The last one, oh, does anybody know why this might be called Q? It's not Latin. I'll give you that. Q stands for quotient. What does quotient mean? Division, right? And that's what fractions are, right? They're a division, or a fraction is a division of integers. So that's where the Q is coming from. And in particular, the reason that we need Q there instead of R is because we already have a meaning for R. R are real numbers. And I know, and it really, it sort of, you could draw these like in consecutive circles going outwards, right? The insidemost circle in your book does this with, I think they do rectangles, but the insidemost circle is natural numbers, and it gets a little bit bigger for the whole numbers, and then a little bit bigger for the integers, and then a little bit bigger, you know, the circles, just these concentric circles like nesting dolls or something like that, okay? Real numbers is our biggest all-encompassing number system that we're going to use. So you get rational numbers, right, all the ones we just talked about, those fractions, but you also get the pi and the square root of 2. You get those kinds of numbers as well. You get E, for those of you who've worked with compound interest before, and you've seen the letter E used. You get that one. What you don't get, and if you haven't seen these before, you can just ignore what I'm about to say, but some of you probably have, is you don't get imaginary numbers. The letter I, that's actually the number, that's not considered a real number. It's an imaginary or a complex number. So those are sort of outside the realm of what this category is describing. But these are the symbols that we're going to use for our different number systems. So taking a look then, this says to write the set of all natural numbers less than 5 using the listing or the roster method. And it says natural numbers, so be careful that you're abiding by whatever system they're giving you. So the listing or the roster method is where you actually list them all out. So what is the smallest natural number less than 5? 1. And then we're going to keep going until I get to what? 4. Because it said less than 5, so I don't want to actually include 5. So 1, 2, 3, 4 in the curly braces, and I'm done. That's the roster method. And for this one, this is definitely the simplest way to write this, right? I mean, there's 4 little numbers I wrote down. Didn't take me any time at all. But for the sake of seeing what it would look like, we're going to do the set builder notation as well, because there are cases when that's a better way of doing it. So set builder notation, I would write down the X, or again, choose your favorite letter if you want, X, vertical line. So X such that X is less than 5, and X is an element of the natural numbers.
When will we use this? Like the set builder notation?
You will sometimes see things written this way in a book. Your book that you're using right now will write something like this, and to knowing what they're talking about. A lot of definitions with mathematics will be defined with this type of notation. And so it isn't so much, Hannah, of being able to use this notation to write something as being able to read it.
Well, we have to like put it into normal terms?
Put it into, go from here to here? You could.
Yeah.
You could.
So if we were doing that, it would just be X. Like, I don't get how you would change that.
These two things right here are identical. So like if we started out right here and you were told to write the listing method, you would write this one down.
Okay.
These are equivalent they're equivalent notations, they're equivalent sets, they're just expressed differently. All right. They're not even equivalent, they're actually equal. Equal sets. I used a word kind of funny there. Equal sets are two sets that contain exactly the same elements. Exactly. Okay, those are equal sets. I'm going to give you a contrast in this in a minute. Let me keep going though for now. A one-to-one correspondence is a pairing of elements between two sets such that each element of one set is paired exactly with the elements of another set. So one-to-one correspondence means they have to have the same number, right? If I have 5 people in my family, you have 5 people in your family, then we can somehow pair people off one-to-one. And then equivalent sets are two sets for which there exists a one-to-one correspondence, right? That's the idea that they have the same number of things. So two sets are equivalent when they have the same number of elements. So let me give you an example. I have 6 people in my family living in my house kind of thing, right? There's 6 of us. I have brother-in-law and sister-in-law, and they have 6 people in their family as well. 6 in my family, 6 in their family. All right? That means our families are equivalent sets. because we have the same number. But they are not equal sets, right? However, if it were the description of it being my family and my husband describing his family, those would be equal sets because we're describing the exact same 6 people. Okay, so equal actually means exactly the same. Equivalent's going to mean, which sounds funny because we've used the word equivalent to mean equal in the past, right? But equivalent for mathematics in logic means they just have the same number of items. All right, so here's an example about one-to-one correspondences now. So it says, how many one-to-one correspondences are there between 2 sets with 6 elements? So if we get together, my husband's, my family, and my sister-in-law's family, there's 6 in each set. How many different pairings could we pair people off in? That's the idea, okay? So I'm going to change it up just a little bit because it's a little bit more fun to do this one, all right? So let's imagine that you went to a mixer and there are 6 ladies and there are 6 gentlemen. All right? 6 ladies are one group, 6 gentlemen are the other group, and the question is how many different pairings could you have? All right, so all the gentlemen are in the room, all right? And the lady comes in and she gets her pick. Because that's the way it should work, isn't it? I agree. So the lady comes in. How many choices does lady number 1 have? She has 6 choices, okay? So I'm going to draw this out kind of like this. These are my 6 ladies. So the first lady comes in, and this lady, she has 6 choices for how many different gentlemen she could leave the room with. Like in theory, she could leave with nobody, but we're pretending that's not going to happen, okay? She's picking somebody, all right? Second lady comes in. How many choices does she have? 5. She can't choose the guy from before, right? That's a no-no. You don't steal somebody's guy. That would not end well. So we have 5 choices for young lady number 2 that comes in the door. Young lady number 3 now comes in the door. How many choices does she have? 4. And we see the pattern developing very quickly. What do I put in my next 3 lines? 3, 2, and 1. And what we need to do with these numbers is we need to multiply them together. Okay? Because once the 6, just imagine, just take the first 2 people. The first person that came in had 6 choices, and the next person had 5 choices. Well, that means she could have chosen any of those 6 people, and the next lady could have chosen any of the next 5 people. There were 5 people that were chosen, or 5 pairings that were chosen because she chose person number 1. If she had chosen person number 2, there would have been 5 different pairings that would have developed. 5 different pairings for person number 3 and so forth. It becomes a multiplication fact. So if you were to multiply 6 times 5 times 4 times 3 times 2 times 1, yikes, is it any wonder it's hard to find the right person? That's only 6 people. Oh my goodness. All right, so there's 720 correspondences.
I feel bad for person number, the last person.
I know, right?
They don't get a choice.
They don't get a choice.
It really is like The Bachelor if you think about it.
Now,
It's crazy.
let me change things up and just imagine for a minute what would happen. Let's say, for instance, those 6 gentlemen, those 6 ladies still showed up. However, gentleman number 3 and lady number 3 are married. Would it change the ordering of what's going to happen here, like in real life sense? Well, of course it would. We wouldn't actually have 6 choices for them, right? There'd be 1 choice because they're already married. There's no more pairings to be happening. So there are conditions that sometimes are put upon these correspondences that you have to be aware of, right? So there could be other weird things too, like 3 of the gentlemen are blonde and 3 of the gentlemen are redheaded, okay? And lady comes in and she absolutely hates blondes. I don't know why, but she just does. Well, that's a condition upon which her number of choices are limited, right? And your book's going to do much more boring examples than that with like letters and within numbers and stuff. But that's the idea. Be aware of the conditions. The conditions will change how many choices something has. Yes, ma'am?
This feels like a permutation.
It is.
Okay.
It is. We're not talking about that, but we do that in proportional statistical
Okay,
reasoning.
'cause I started
But
saying
it
that. I
does.
was like,
Yeah.
wait, I'm confused.
Yeah, it is.
Okay.
Okay. Now, cardinal number is what we call the number of items a set has. Okay, however many items are in a set, that's called its cardinal number. And the way that we write cardinal number is we write the letter N with the set that we're referring to next to it. So if the set is capital S, N of S means the number of items in the number of elements, we'll say it that way, in set S. That's what it means. N of S means the number of elements in set S. So if I were to do my family, the number of elements in my family is 6. Okay? All right, a finite set. A finite set is a set for which the cardinal number is a whole number. In particular, it doesn't necessarily mean the number of items that can be counted, but that they really do have a designated finite, a designated number for which you could get to if you could count them all. So like imagine when, God tells Abraham to count the sand on the seashore. That's not really a possible task, but there is an actual number of the sand grains on the seashore, right? So that's a finite set, a huge crazy number that we could never actually get to if we counted it, but it's finite. Okay? So finite doesn't just mean not huge. It means there's actually a number that I can assign to it that actually is the value, okay? Infinite now says it's something that you don't have. It's not possible to do that with it. Okay? So an infinite set, for example, that you're aware of, and you probably didn't know about it, is the set of real numbers, or even the set of rational numbers. We'll do rationals just because it's easier to talk about. Rational numbers, all those fractions. Anytime you give me two fractions, I can find one in between them. There's infinitely many. There's no possible way that you can list them all out, even if you had all the time there is. It's not possible. There's always one in between every two you find. It's infinite. The null set is a set that contains no elements. Its cardinality is 0. There's multiple ways that we can write this. One way is a 0 with a line through it like this. Okay, so some of you probably write your zeros like that. Now's the time to break that habit because it really has another name. Don't write your 0 with a line through it for the number 0. The 0 with a line through it has two meanings in mathematics. One of them is this one, means null set. Does anybody remember what the other one is? You see it more in algebra. Empty set's like this one. It's null set, empty set. Close, no solution. So another meaning of the 0 with a line through it is no solution. And these are related ideas, obviously. So when you put the 0 with the line through it, it means it's something for which you can't count it. And you might feel like, well, that's kind of a dumb thing to even describe. But what we're going to do next is we're going to do just that. I think that's my last example on this sheet, so we're going to just flip because it's fun. Okay, so go to the, oh, what's another one? I'm going to give you one. Hang on. Of a null set? Yeah, I'm going to give you one. I want to show you one more notation. Another notation for a null set, is the curly braces where you don't write anything inside of them. Which kind of makes sense. It's kind of a silly way of putting it down, but it works. Okay? Now, if you talk about the cardinality of this, cardinality is defined as when you write the n with whatever's in parentheses, of the set next to it. Cardinality of this is 0. So I know this notation looks kind of funny, but this is saying the number of items in the empty set is 0. Number of items in the empty set is 0. So here's what I'm going to do. I'm going to give you an example, and then you're going to flip to the very last example in your notes, and you're going to write yourself down an example. Okay? Here's an example. I'll give you the example I used to give until about 3 years ago, because I can't give this example anymore, and then I'll give you a new example. I'm going to talk about how amazing and wonderful the babies are that live in my house. They're fantastic. They sleep through the night. They eat all their meals. They never cry. They're just the best babies that exist. Because that set is an empty set. I have no babies in my house. This is the example I use now. I used to use the teenagers in my house. Now I have teenagers, and now most of those things aren't true anymore. I have problems because they actually exist. So yeah, you can talk about something and you can actually have something where you're describing pieces that don't exist. Now, if I talked about the babies in my house and some of you talked about the babies in your house, they might exist in your house. It might not be a null set for you, right? You may have a younger brother or younger sister. I know Cortland has a daughter, right? I mean, so the descriptions would be different depending on who's describing what set. Okay? So I want you to write down, this is example number 11, and I'll give you another one too just for fun. For me. Create a real life example of the null set in your life. Okay? So we'll take just a minute or so and try to find something. A null set in your life. So mine are the babies in my house. It's a description of a set that has nothing in it in your life.
Okay. Ooh, do we describe it like you did?
You don't have to say all those words. You just describe it. Like if I were describing mine, I would put the little curly braces and I would say the babies in my family. Or something like that. The babies that live in my house.
So just
Yep, do the little curly braces and you can write a description inside. Some of you are smiling. I can tell you write down funny things. Okay, does somebody want to share what they wrote down? Okay, Emily?
I said the boys that I want to date it over you.
The boys who want to date it over you. Fabulous. Leah?
My two's not funny, okay.
Okay.
I put braces on people in my immediate family.
That's good. Braces is good. Glasses might be some for some families too. Not, well, in my home it would work actually. So
I put the wonderful boyfriend who buys me nice things.
the wonderful boyfriend that buys you nice things. That's fabulous. Amy?
I put the sports team I am a part of.
The sports team I'm a part of. That's very good. Okay, any others you want to share? You don't have to, but
I put the redheads in my family.
redheads in your family. Fabulous.
I put the 5 toes on my right foot because I'm missing some toes on my right foot.
That's fun. Very nice. The one that I had thought of while we were standing here is the monsters in my son's closet.
Yeah.
Does anybody have monsters in your little brother closet or something like that? The monsters in my son's closet. You have them in your house?
Yeah, apparently.
Evidently. I was told the other night to make sure the closet door got closed actually so the monsters wouldn't get out. All right, let's go back and take a look at, let's see where we are. Venn diagrams? Nope. Cardinal numbers. There we are. All right, so what we're going to do next is we're going to find the cardinal numbers of a few sets. So cardinal number, again, just means how many of them, how many items are in them. So for the sake of making this simple, I'm going to call this set A. I'm going to call this set B. I'm going to call this set C, and I'm going to call this set D. Okay? And the reason I want to do that is because I want you to see that you notationally can talk about N of A. And N of A means the number of items, the number of elements in set A. So, you guys got pretty good at counting elements when we were doing Gauss's method, right? So, thinking back to that, how could I find the number of elements from 9, 10, 11 up to 99?
99 minus 8.
Right. So, this would be 99. Actually, I'll write it over there. 99 minus 8, which is what? 91. The cardinal number of set A is 91. Okay, on set B, we're skipping some, right? Exactly how many of them are we skipping? Yeah, like every other one, like half, right? We're skipping half of them, basically. So what would I have to do to find the number of items in this set?
202 minus 0.
Okay, and you could do minus 0 and then over 2. So it's 2002 minus 0, and 0 is happening because it's the next item before 2, right, in the pattern. So it's minus 0. And then dividing by 2 because I'm skipping every other one, right? Yeah. All right, so what would I get for this one? 1001. So do I want to write down all 1001 of these elements? Well, no, of course I don't, but it is still finite, yes? It is still a number of items that could actually be counted.
So what exactly is the cardinal number?
Means the number of items in the set. Just means how many are there. So the cardinal number of my family members is 6. Yes?
Just so I make sure I'm understanding, you did this minus 0 because 0 is before 2, would have come before 2.
Correct.
So if we would have started at 4, then it would be 2002 minus 2?
Correct.
Because that would have come before 4.
Yes.
Okay.
Exactly. Okay, C. Now C and D are both written in that funny set builder notation, right? Please don't let that throw you. It's not really intended to, but it is intended for you to try and figure out what this set actually is. For example, this set on C is the set of the numbers that are x squared, and all of the x values that it uses are 1, 3, 5 up to 99. So this set is really like it's 1 squared and 3 squared and 5 squared all the way up to 99 squared. Okay, that's all it is. Okay, that was too big on my eraser. Hang on. Okay, so does the squaring actually matter? No, it doesn't change how many items are there at all, does it? No, it doesn't. So when I'm counting the number of items in the set, how do I find the number of items, the cardinal number of set C?
99 minus -1. Which would be 100, and then you divide by 2.
Yes. Okay, so this is 100 divided by 2, or 50. Okay, so Amy, you said minus the -1, and you're correct. Why did you choose to subtract -1?
Because you have to do the first number in the pattern, and the pattern is going by every other number. So you're not going to use 0 because that's the number directly before 1. You have to skip over 0 and use the number.
Right.
next.
This pattern is every other number, right? So the number in the pattern, if it came before 1, would have been -1. Now, that's a very, very good description. The other way that I'll sometimes describe this is that really this is like all the numbers from 1 to 100, just the odds. So you could also think of it that way. It's all the odds between 1 and 100, which is half of them. It's 50. It doesn't work very well to describe what I just did if it didn't start at 1. But because it starts at 1, it's kind of nice to describe it that way. Okay, last one on this page. This one says the x value such that x is equal to x plus 1. It says x is a natural number. Okay, so what would happen if I thought that maybe x could be 5? And I tried to do this. I tried to say 5 is equal to 5 plus 1. What's going to happen?
Not going to equal each other.
It's not going to equal each other. Like, ever. Right? This is a null set. This is a set with nothing in it. There are no numbers that solve that equation. Think about it from an algebra standpoint. If you tried to solve this equation, what would you do? Well, you would subtract x from both sides, and you'd get 0 on the left and 1 on the right, and you would say something like, not possible, no solution, doesn't work. Same thing's true here. There are no numbers for which that equation is true, so there are no items in this set, just like there's no babies in my house and no monsters in my son's closet. So the number of items in set D is actually,
Empty set.
it's the empty set, but the number of items is 0. Okay, do you see the difference in the notation? This whole set is the empty set, but the number of items in set D is 0. When we write down cardinal number n of something, we get a number when we're done. When we write down a set, we describe what the set is. That's the empty set notation. Okay, let's do one more slide and we'll stop, okay? Venn diagrams. We're going to work a lot with Venn diagrams in the next couple of sections, so let me first just talk about what they are. A Venn diagram is simply a diagram used to illustrate an idea in logic. Okay? A Venn diagram starts out with a rectangle. So in some space, beside, beneath, whatever, I'd like for you to draw a rectangle on your sheet of paper there, on your notes. Like this. I've got a rectangle. That rectangle is understood to be my universal set. A universal set is a set that contains all elements being considered in a given discussion. So if we're talking about the universal set U as the people in my family, then everybody's names could be written inside that rectangle. I'd have 6 people. Okay? The complement of a given set F is all elements that are not in the set. So let me actually draw a set inside of this. So this is set F. And it's, okay, that's not what I wanted to do. Let's try again. Let's give that a shot. Okay, pink. That set F right there is whatever description I'm using. So if the universal set is all the people in my family, and F are the females. Okay? So inside my circle would be myself and my 2 daughters in the circle. What would be on the outside, and still inside the rectangle, but outside of my circle?
The male.
All the males, the men in my family, my husband and my 2 sons. So out here, we call this F complement, and your book uses the complement notation that's a bar on the top. Okay? There are a couple other notations. Your book is going to use the bar on the top. Let me show you a couple other notations just in case you were seeing this inside of some other resource and you were like, I've never seen that before. Sometimes it is written, oops, I'm sorry, with a little C up here. That's the least common way I've seen it, but I have seen it. So F complement. It's actually a really nice notation. It's very friendly. And another notation is to put sort of a accent mark or an apostrophe or whatever. Okay? So, or if you've seen something with calculus, sometimes we call that a prime notation instead of calculus, okay? So those are the 3 notations. Our book's going to use bars on the top, so we're going to use bars when we discuss it.
So how is that different than like a tilde be like not?
It's just different notation for different items. This is set notation. What we were describing before was argument notation. Yeah.